Thank you, Mr. Wu, for the inspiring speech. Jarry has always been a professional manufacturer of motion control and systematic technology, and it has also been highly involved in the electric vehicle industry. For the trend of semiconductors, automotive components, and welding, Mr. Wu all provided in-depth discussion. I believe his speech can bring inspiring ideas to all of you. For the second session, it's of our great pleasure to have Chief Officer of DFI, Mr. Jarry Chang, to be our speaker. Mr. Chang is adept at leading product planning from the aspect of key application and has also developed innovative designs that are widely used in industrial automation and electric vehicles. Today, he will talk about edge computing and cloud management for AIoT of EV fleet. Please welcome Mr. Jarry Chang.
Hello, everyone. I'm Jarry Chang. I'm currently the Senior Director at DFI. Today, I'm very happy to be here and talk to you about the Internet of Vehicles on the subject of fleet management. When talking about the Internet of Vehicles, the first thing to know is the Internet of Things, or IoT in short. We all know that the core concept of the IoT is that everything is connected, and different industries may have their own IoT. So let's first take a look at the differences and similarities between different IoTs regarding architecture, development, and technology, and see if there's anything we can learn from. For the time being, smart power grid is of relatively mature development. There are several aspects worth discussing about this application as references for future development of the Internet of Vehicles for IOV or the artificial intelligence of things for AIOV, since there might be a similar architecture or some structural changes. So, one very important point is called decentralization. In the past, electricity generation relied heavily on large nuclear power plant or thermal power plant. Electricity was transmitted one way through a dense network and thick cables to various places. But an important thing about the smart grid is that it's a decentralized system. Nowadays, it's not just mere thermal power or nuclear power. There is also an integration with a renewable energy, such as solar power or wind power. So we can see that smart grid includes distributed energy resources, or DERs in short. And secondly, its diversity has also increased. It's different from how it was done in the previous era, when it's more of a centralized way. And this has a lot to do with the technology and the cloud applications that came along with the Internet of Things. The third one is the integration of heterogeneity. There is a very important property about smart grid, which is it integrates different electricity generation methods and features. For example, every kind of electricity generation method, thermal, hydro, or solar energy, has different electrical potential and even different medium. So, how is the integration done? Let me explain to you by the case of solar power. For housing power generation during the daytime when there's lots of sunlight, solar energy can provide enough electricity input to the entire power grid. And then at night, when the sun goes down, electricity output will be switched to thermal and nuclear power. It means that the smart grid can do both input and output, and electricity can be transmitted in both directions. This also applies to the electric vehicles, as it may be a device that needs recharging, but it can also be a power supply device under special conditions. So, as the heterogeneity between these electricity generation methods is very strong, the power grid needs to have excellent flexibility to respond to such changes. And that's the development changes and architecture modifications that we can see in the smart power grid. So, here comes another point. When artificial intelligence is involved, things become different again. AI brings revolution, and it reverses and even completely changes the original application of certain industries. And because of this technology revolution, we have to start thinking about the structural revision and modification that we mentioned about smart power grid. And we also need to think about decentralization, whether it is for the IOV or other industries. What DFI provides is server platform and also cloud computing. And cloud computing is actually facing the challenge of connectivity, such as bandwidth limitations and latency issues. Even when we enter the 5G era or 6G era, data is growing endlessly. And the image we see will also be enhanced continually to the next level, just like we are now starting to talk about 4K or 8K resolution. So, no matter how the future is going to be, we will all encounter a situation which is that the amount of data transmitted will become bigger and bigger. And it's highly possible that a centralized data center will face bandwidth problem, regardless of how high it may be. And there will surely be impacts on execution efficiency. Back to the time when the Internet of Things was first introduced, we were all very used to think from the perspective of the cloud, using cloud to plan the whole architecture. But now the smart power grid has already told us that the open and distributed architecture will give us more efficiency, and the system itself will be more flexible. Let me share a case with you. This is a recent news. Google say that they will start downsizing its health teams and slow down the pace for the business. And at the same time, IBM was also reported to consider selling its famous Watson Health unit. So, what's exactly happening? Is there something wrong with the remote health system? From what they say in the reports, it's not the main reason. The reason why these were technology leaders made such decision was that both Google and IBM involve artificial intelligence technology in their health teams. And the problem they both encountered was that the actual healthcare environment is not yet able to support the loading of the high-tech health systems. So this is actually a critical issue because when AI is introduced into the IoT, we need to think about whether connectivity will become an obstacle in the whole process. For example, what IBM's Watson Health is often criticized for is that to send back diagnosis results, the diagnosis itself must be uploaded to the cloud first. And this will actually cause the efficiency to decrease and make the implementation process more time-consuming. So, when it comes to artificial intelligence of things, or AIoT in short, we must take this issue into account. Since we always want to pursue better performance and connection speed, the issues that were mentioned above will surely be challenges. Both IBM and Google developed their system based on the cloud, so they will want to do cloud computing for all the data. And that's why the topic we are going to discuss today is that in the new era of IOV, we can't just rely on cloud. And of course, neither can we only keep the computing at the edge. What we need is a coordinated and collaborative model. And it is related to the concept of distributed architecture that we are going to talk about today. When we talk about distributed architecture, it's required that the edge server has the computing ability, which is called edge computing. Through edge computing, a computing grid will further be generated. And then you need to optimize the grid to acquire the best performance. It is actually similar to the practice of smart grid. That is, you can compute data by either edge computing or cloud computing based on the most efficient condition to achieve loading balance. Take facial recognition, for example. If we upload all the high-resolution images to the cloud, it will take quite a long time for transmission. So now more and more are using edge computing for facial recognition. What it does is after a face is detected, the image of the face will undergo simple computing at the edge first and only transmit the face features to the cloud. Suppose you have 1 million people to recognize. The database of these 1 million people will be built in the cloud. But because the process of capturing and computing the features of these faces is already finished at the edge, there will only be eigenvalue left. And they are so small that they may be computed in mega units, not like the high-resolution images, which are calculated by the gigaunit. So you can see that it's a quicker and also more efficient solution. And therefore, edge computing is bound to play a crucial role in the future of Internet of Things and Internet of Vehicles. So, as what I just mentioned about connecting everything as a group, it's also the point of IoT, which is building a network of things. Then we have to think about how to connect everything together in our software environment. And after the network is built, whether it be the smart grid or the Internet of Vehicles, we will then encounter an issue, and that is the so-called heterogeneous integration. So we have to first think about the obstacles and challenges we might encounter in the future. We need to prepare ourselves for those challenges and adjust the architecture beforehand. DFI has currently been cooperating with Ubuntu, a Linux operating system provider. And what Ubuntu is doing is called containerization. Along with virtualization, containerization is also one of the things we should focus on when developing the new IoT in the future. So, containerization is defined as a form of operating system virtualization, through which things like kernel, API, UI, your customer's data, or custom data are packaged in isolated user spaces called containers using the same operating system. In short, if a great amount of data is allocated to several containers, then it's called containerization. It's pretty much the concept of module. Now, when using the iPhone or Android phone every day, you often encounter one situation, which is that they will remind you to update your operating system. And there is already a containerized architecture inside. So you don't have to worry about updating the operating system, for example, from iOS 13 to 14, will cause your data to disappear because the data architecture has already been containerized. So why do we need containerization? For the previous IoT era, when AI hadn't been introduced, IoT could disable the operating system update. Disable means that the operating system will be maintained in the original version. The situation may be that communication with the outside world is not required, or all the work can be done within a small range. So in that case, maybe no operating system update is needed during the whole product life cycle. But when time comes to the era of AIoT, the artificial intelligence of things, this way will no longer be feasible because AIoT has a key feature, which is the ability of inference, or the AI model, and it improves with the times, so it requires constant update. Just like the current self-driving system, Tesla tells its drivers from time to time to update their software, and because of this, connection to the internet and periodical update will be a must. So it's necessary to do containerization. For if we don't, we'll have to recall products for testing every time there's an update, and that is just totally infeasible. So the first point is that we need to containerize the whole architecture, and we have already been working with Ubuntu regarding this. Some of our certified systems and products are already available on the Ubuntu website. In the future, we will also continue to have more of our products certified under the containerized environment and build a more mature update environment. Here we have a product named Remote Guard. It's a cloud management platform that gives real-time dynamic view of your device's status. So if you encounter a disk damage situation during the update process, as long as it's not completely damaged or just some sectors are damaged, causing the operating system not able to be booted, the Remote Guard, which we developed with InnoDisk, can copy your image data directly from the backup of the sectors and reboot the operating system. We are now planning to adopt the OTA architecture, which is a mechanism for remotely updating our customers' firmware and software, and ensure that in the case of sector failure, the entire sector can still be updated or restored. It will be a challenge in the future. And so the first key point is containerization and remote cloud management that can recover sectors and reboot them again. And this is the field we are currently working on. The second thing is that, on account of the increase of heterogeneous integration, multiple operating systems have to run simultaneously on the same infrastructure. So we need to think about how to virtualize the environment. Virtualization is actually a technology that has existed for a few decades. In the past, it's mostly used to create virtual CPU and virtual memory, which means you might have 3 or 4 operating systems in your server, but basically the I/O is shared. The monitor, keyboard, mouse, and LAN port are shared. And now Intel is introducing a new virtualization technology, using hypervisors to abstract hardware and enable a variety of workloads to co-locate. That means different I/O can be assigned to a specific operating system. So why do we need virtualization? Because we want the operating system to be gradually neutralized so that hardware and software don't have to be taken into account when the users are selecting hardware in the future. Let me share a case with you. Some of our customers need Windows XP to run specific I/O. Many people know that most new hardware don't support Windows XP anymore. And what we do is we help them build a virtual machine to run the operating system independently. So this is one of the examples about how we can help our customers to do heterogeneous integration and through virtualization have more flexibility in the future. In addition to this benefit, you can also put multiple operating systems on the same virtualization layer, meaning you can use one piece of hardware to run different operating systems, but also have independent I/O. This is one of our demo kits. We apply the Intel Acrom hypervisor with 3 displays. We use 3 sets of different I/O, 3 monitors, 3 keyboards, and 3 mouses. And then we run 3 operating systems at the same time. So these 3 operating systems are actually run in a completely independent way. In other words, if 3 people are using these 3 computers at the same time, they will not know that they are actually sharing the same motherboard. And that is what virtual technology can already achieve. It abstracts hardware for several hosts to share. And it makes software and hardware more neutral in terms of adaptability. So why do we need this technology? Because as electric vehicles develop, with different levels of autonomous driving coming out, like level 2, level 3, level 4, what we understand as driving will gradually change. When we sit in the vehicles, we will spend less time driving and more time doing other non-driving behaviors. That is to say, future vehicles, whether it is a bus or a sedan, they will slowly become a recreational space like a living room. And because of that, when the role that entertainment is playing in vehicles becomes more and more emphasized, how can we apply the hypervisor that I've just mentioned? What we can do is that we can use one hardware to run 4 monitors. So we have one dashboard which is mission critical, responsible for the main driving function and safety system. And then we use the hypervisor to connect the other 2 in-vehicle infotainment systems of the front and rear seat. So it's not mission critical at all. It's just an entertainment platform. And through this architecture, I can let different users watch the content they want independently. But why not use 4 pieces of hardware? Because in the future, we will encounter a situation in automotive applications, which is the yield will be inversely proportional to the amount of hardware you use. Simply put, the more hardware you import, the lower the yield will be. So, using one single powerful hardware to run four independent operating systems in virtual environment that allow four users to use through independent I/O, or using four independent hardware to do it, it's a four-time difference in yield. And that's why in the future automotive industry, with more parts, more electronics, and higher complexity, virtualization can be a helpful and efficient technology to maintain the yield. Then let's move on to today's main subject, which is fleet management. First of all, there are two major points in fleet management. The first one is the cloud management of electric fleet, and the other one is the most optimized charging method. So first, let's discuss a bit about why charging is emphasized. This is the charging time chart of Tesla's Model Y. Let's look at the bar graph first. For the orange bars, we can see that charging from 30% to 80% only takes less than half of the time in the whole charge cycle. The whole charge cycle is more than 2 hours, but 50% of the capacity is charged in 51 minutes. And this is actually a very normal situation. Let me explain a bit more through the line chart above. We can see that this charge curve is somehow special. When the charging starts, the voltage rises slowly, and the current remains unchanged. But when a battery is almost fully charged, the voltage will climb fast. And that's because as the battery level gets closer to full charge, the voltage needed will increase. So the current must go down. Otherwise, the problem of heating up will happen. And the most important thing is to maintain the battery life. So this means that if you charge the battery to a certain level and keep charging it, the efficiency will surely slowly decline. You can still overcharge your battery, but you might end up damaging it and reducing its life. So a good battery management system will slowly lower the current, but at the same time, it means charging will be less efficient. Why is it important to electric vehicle fleet? Because a fleet does not just have one vehicle. If it's just one RV, the driver can just have a coffee, read a newspaper, play with his phone while waiting for the battery to be fully charged. But what we have to consider here is the situation for a fleet. And a major point is economic efficiency. Fleet has to make money. So in that case, you cannot leave your car with less than 30% or 20% of power on the road, because if any unexpected incidents happen, the car may not be able to return. And it will have to be towed or through other methods to get back to the charging station. So you have to make sure your vehicles are back to charge when there's only a certain amount of battery level left. But meanwhile, you don't want them to be fully charged because it is not efficient. What you need to do is charge them to a certain level and then they can sit up again. So what's the exact level to be charged and what's the most efficient way to do it are decided according to your knowledge of how far the vehicles will be driven. And then based on these different distances to make corresponding calculations. So the management will be very complicated. And speaking of management, a complete and functional system is a must. And this is what we are currently working with MaxWing, a leading solutions provider for intelligent transport systems in Taiwan. So since it's called Internet of Vehicles, in the future, whether it is self-driving or with a driver, connection to the internet must be made with the device within the vehicle, a tablet, a phone, or through different applications like WeChat or Line. We must have remote communication, and it requires a management system to send notifications or give orders. And that is something fleet management needs to do as well. So back to what I just said, we have to manage the charging. And when you are doing your charging management, you will need to do it by remote communication. You need to know very timely about the status of each vehicle in your fleet. And you need to know their real-time state of charge. Otherwise, there's no way to do management well. So you must be able to calculate through the cloud which vehicles in the fleet will need to be charged after they arrive at certain locations. And also, you can understand the current road conditions through real-time images. and then plan how to do your charging management. Therefore, we can basically say that charging is one of the most important issues in the future of electric vehicle when it comes to the fleet management. The first thing about charging is that you have to know which charging stations are in the area where your fleet is running. And then you have to know which vehicle needs to go to the nearest charging station before its battery falls below a certain state of charge. Then, to what level the battery is charged and how far the next destination is, all need to be taken into account when you calculate whether the vehicle has the enough electricity to arrive the next charging station or destination. So you need to have a cloud to do this very complex management. Otherwise, you will find your vehicles spending most of their time looking for charging stations or stopping at the road because they run out of electricity. If a car only needs to be charged to 70% to arrive the next stop, it doesn't need to be charged to 80% before it sets off. You need to manage in time and send command like charge to 70% and then set off to a car if such level of charge is sufficient for it to arrive the next stop. This management is done through the cloud, and edge devices receive instructions. Whether it is a self-driving car or a bus with a driver, the fleet management system has to become a grid where cloud and edge can work with one another. Let's dig a bit deeper at the edge. As mentioned earlier, everyone is talking about autonomous driving. But in fact, when it's applied to electric vehicle fleet, whether it's a truck or a bus, it's a lot more difficult because they are larger in size, which is why it's more complicated on safety control and there are more aspects that must be considered. In addition to the general function that the systems of vans or sedans will have, such as lane departure warning or ADAS, because trucks and buses carry heavy loads, their tires wear out faster too. So it's also necessary to include the monitoring of tire pressure. The next one is a situation called the difference of radius between inner wheels. The difference of radius between inner wheels is a blind area caused when a heavy vehicle makes a turn. We often see accidents happen when the driver isn't paying attention or a passenger or rider rushes into this dangerous gap. So in the future, we have to realize what's called prevention is better than cure. And it can't just be a pedestrian guide or lifting the public's awareness. As long as there is other vehicle, pedestrian, or anything running into this area of radius difference, response like warning or stopping at once must be made immediately. This is the future of fleet management as well as self-driving vehicles, and edge computing will become more and more complex. Other things like recording, prediction, or fatigue detection will also need to be computed at the edge in the future of automated vehicles. We talked a lot about edge computing today because it's a booming trend that we see in the electric vehicles. It has been 40 years since the FI was founded, and we have been developing industrial computers for nearly 20 years. For the field of electric vehicles, in fleet management and edge computing in different applications, we have developed and provide many related products, and we also have many experiences that we can share. As I mentioned earlier, edge devices nowadays have to be resilient. In the past, when we talked about IoT, we didn't focus much on high performance because we basically just connect everything together. But now, with the adoption of AI, whether it's smart driving or smart charging, the performance of edge infrastructure needs to be more robust. And with the edge also going for virtualization, we need better integration, conveniency, and flexibility. In addition, miniaturization is of great interest to many customers when they select a platform. Durability and ruggedness, such as wide temperature, waterproof, and pressure resistance, also play crucial roles in their decision making. Let's first talk about miniaturization. DFI has made the mainstream CPU of Intel and AMD into a business car sized, like the Intel Apollo Lake with a nearly 10 watts TDP and the AMD VR1000 with a 10 watts TDP. And we also found that it is a lot easier for our customers to access AI regardless of the location. And because performance is not equal to the actual volume of the product, there's no need to produce a very large machine. So for now, we have this simple AI accessible board, and we are also on our way to develop more flexible platform. Besides the 10-watt CPU, we also provide a desktop CPU. The performance of this Intel desktop CPU is more powerful than the other two platforms, and we managed to maintain its size to be a 3.5-inch hard disk size, just exactly the 3.5-inch size like the traditional hard disk. And we put the platform inside so that our customers can easily integrate this high-performance CPU in the device or the field they need. We have also extended the operating temperature because this design is for more specific applications. For example, in the case of IOV, temperature will be a great challenge for in-vehicle system, whether it is placed in the car or on the roadside. So this is a great consideration in our product development. And what we do with the AMT platform is that it's the same 3.5-inch size, and it can be connected to 4 monitors. So, for example, it can be used in the in-vehicle infotainment system that we talked about. And this is a common application in the Internet of Vehicles. It's called the law enforcement done by AI technology. For example, the platform can be installed on street lights or traffic lights to do traffic flow analysis, and then send the data back to the Internet of Vehicles so that the whole network has more sufficient information. And it can also be used for the fleet management that I mentioned earlier. And this one is an application from our customers in the Netherlands. They use the Intel 10-watt CPU that we have just talked about in police cars in-vehicle system, mainly to record vehicle registration plates of traffic violations or unexpected situations, and then send back the data. This platform also supports dual SIM cards because in Europe, there's often a need of switching SIM cards between different mobile providers when crossing regions. So we provide this customized service to enhance the flexibility of the Internet of Vehicles. This is the case of our customers in Nordic countries. What they required was tablets with screen, but the things they do is similar to that of the police car in-vehicle system. The difference is that the police need to take the device out of the car to handle traffic violation, and the recorded data will also be sent back to its cloud system. This is an application for buses also in Europe. The touch panel is directly embedded in the system, and there's also many applications related to the cloud. In the future, when there are more and more electric vehicle fleets, whether they are buses or trucks, there will be a need for passenger surveillance. Because assuming it's an autonomous vehicle, the system will need to monitor the passengers when there's no driver or the driver is taking care of other things. The purpose of passenger surveillance is to protect the passengers and reduce risks, responding to situations like passenger fainting, unexpected accidents, or someone causing a disturbance. These are the situations that require in-time surveillance through AI technology to know whether a person is just walking, or he's already fainted, or he's in argument with someone. This is what the AI model can do, and after the data is sent back to the cloud, response can be made immediately. If it's installed in a truck, you can design the system aiming for cargo management. Related functions may include anti-theft or intrusion prevention. These are all the applications this platform can do. With the Intel Core i7 CPU, it's very powerful and also robust in AI performance. Besides EV fleet, trucks, and public transit, There is another very special and also vital application. This is an autonomous road sweeping vehicle. It can function as a cargo truck and also a street cleaner. This solution is currently very popular in China, and they hope to realize the vision of unmanned public space cleaning in the near future. That is to say, everything will be done by this autonomous street sweeper. We just have to ensure that it won't hurt people, it won't hit any objects, and most importantly, it can really clean. This is the platform they used, and as it's highly performance demanding, we also installed NVIDIA MXM module to enhance its graphics performance. Basically, it's an unmanned vehicle responsible for road sweeping. It's another application of AMR, different from self-driving and EV fleet solution, but also a fast-growing field. So, for different in-vehicle applications, like fleets, vans, or rail cars, DFI provides different products correspondingly. And we also found a trend that transportation applications are receiving more and more attention. And with the adoption of AI and the demand for the Internet of Things, stronger and stronger performance has also been required. There will also be more diversified demand. For instance, for wide footage, high waterproof level, and wide temperature. It's an ever-changing industry, and we keep challenging ourselves, making product line adjustments in response to such changes, so that the market demand can be fulfilled with the right products. The last topic I want to share with you is temperature. We often see news about which place is having record-breaking temperatures of 40 or even over 50 degrees. Even though we hate to admit it, the global climate anomaly is already a new normal. Therefore, in the future, the products that we originally expected will be placed in an air-conditioned indoor environment will have to face adjustment because now with demand for IOV application increasing, we cannot expect the future cars to be placed on the road with air conditioning, which is impossible. In other words, the platform itself needs to be high temperature or splash resistant. It has gradually become a norm, and we are also widening the range of operating temperature from standard wide of minus 40 to 80 degrees to slowly going downward and upward. It is also responding to the challenges that extreme temperatures will bring in the future. We enhance the flexibility of these platforms and make them more resilient to different situations. And finally, back to where we started today and allow me to recap some main points. When facing the era of the artificial intelligence of vehicles, the first thing to understand is that AI is revolutionary. It will bring significant changes, and the whole IT architecture and the platforms needed will also change. So the next thing to consider is the software environment. And as remote upgrade of software and firmware will be required, containerization and virtualization will need to be included when designing the system architecture. Then comes cloud managing, another fundamental part of the future. Not just uploading all data to the cloud, but requiring a very intricate system to do the management. And then you need to come up with an optimized charging system. As edge computing becomes more and more important, your edge devices also need to be improved. And lastly, miniaturization and high performance are also the developing trends in the future. These are the trends that DFI has observed on our way of developing industrial computers and understanding the emerging Internet of Vehicles. And we dedicate ourselves to adjusting our product lines so that we can provide better choices for the industry, and so that our customers can have more suitable and useful products. It's the end of my presentation. Thank you all for your attention.